Good morning, and welcome to our second educational webinar brought to you by WeatherWorks. My name is Nathan Wiles, Lead Meteorologist and Assistant Marketing Director of the company. Today we will be discussing the topic of weather radar and highlighting some important uses and features that will help you stay ahead of changing weather conditions and help you make cost-effective decisions around the clock. In all, the webinar will take around 25 minutes of time and will be followed by a short question and answer session. Feel free to download our radar brochure in the handouts section on the right-hand side of your screen. You may also comment or ask anything in the question panel throughout the duration of the webinar, and we will review some of your questions at the end of this session. Today's presenter is none other than Robert Reale, Director of Meteorological Services. Rob has over 10 years of professional experience as a meteorologist and has led multiple workshops at both SIMA and ASCA in years past. Rob, the floor is yours.
All right, thank you, Nate. And yes, that picture is representative of kind of what I usually look like, but after several months of quarantine and no haircut since February, the live look at me is what you get. So I apologize for that in advance. But as Nate mentioned, we'll be discussing weather radar as well as other sources of obtaining ground truth. And one of the things you'll learn about radar today is what you see is not always what you get. I'm sure most of you have looked at radar and it showed precipitation falling, but you poked your head outside the truck and there was nothing going on. Or the radar says now snow is flipped to rain, but it's still the other one, or vice versa. So we'll explain why that happens and how you can better prepare for it next time. So we'll start off with the basics. In the first couple of minutes, we'll go a little bit slow as we catch our bearings. We'll discuss what radar is and how it works. But as we tie in the differences between a regional composite radar and an actual Doppler radar, as well as some of the intricacies that go into it, I think you'll have a new understanding of what you're looking at and a better idea of how to interpret radar. We'll then tie in additional sources of ground truth, such as webcams and airport observations, with the overall end goal, how to better radar. So we'll start off with the very basics. What is radar? And essentially, it's an acronym standing for radio detection and ranging. It works by sending electromagnetic waves and listening for the return signals. No, these are not harmful waves. They don't contribute to contrails, nothing like that. You'll never see them, but they're mainly calibrated to detect atmospheric moisture such as rain, snow, sleet, and hail, but there are times it'll pick up things such as insects, birds, and smoke from a fire. How does it work? Well, here's a little short little clip of kind of the radar to the left, sending out those electromagnetic waves, and then it listens for the returns. So if it hits nothing, it wouldn't show anything. If it hits stronger returns, which would be stronger and heavier precipitation, you'd have higher returns. So I know in the end, you don't necessarily care how it works. You really just want to know what's the end goal, how can I use it, how can I look at my radar and see if it's raining or snowing or heavy or light. So that's essentially how it works. And on the right is what you get as the end user. How do you radar? I would venture to guess that everyone on this webinar has somewhere between 1 to 5 weather and/or radar apps on their phone, if not more. You could also be looking at the National Weather Service, watching the Weather Channel, looking at social media outlets, using a private weather service such as ourselves. There's so many different ways to view radar. I'm not going to go into every single app and every single method, but I am going to review how you should be viewing radar and how you should be interpreting it. So we'll start with a couple different views of how you could be looking at radar. And one would be a composite view where you're looking at a national or a regional level. There's no one radar that just scans the entire US and gives you this image. What in reality, it's made up of all these local Doppler radar sites, and it's blurred together to get you this one big picture image. So again, there's not one big radar that looks at the whole US. There's a whole bunch of little radars that scan the US that are called Doppler radars, like you see here, that are blurred together to give you this regional composite view. And here's an example of a coastal storm starting to form. We can kind of see this little swirl off of the North Carolina and some precipitation starting to build into Virginia, Maryland, and looks like it'll eventually be into Delaware and New Jersey. But again, this is comprised of multiple of these local Doppler radars, which we'll touch on in just a little bit more in just a second. So sticking with composite radars for now, you can be looking at a regional or a national view. And as we mentioned, it's created using an algorithm to combine a whole bunch of localized radars together. And sure, it's very useful to get the big picture, and it's usually pretty aesthetically pleasing. However, composite radars can be deceiving, and oftentimes they overestimate the coverage of precipitation. Many news station apps and many news stations and many apps show composite radars. So just be aware of that. And I'll give you a quick demonstration of how composite radar is blurred together, and then what are some of the faults of looking at a composite radar. So we'll start with, on the left, we see the Doppler radar. One's right outside of DC with the red dot, and another one's just south of Richmond with the yellow dot. And if we look to the right, the regional composite radar is kind of blurred with both of those radars together, and you can kind of see the coverage area outlined in red and outlined in yellow. In between, where you see them kind of in DC to Richmond area, you can see that there's overlap. So together, they're kind of making this composite radar with both of those radars in mind. So now if we focus on what's happening towards the DC and Baltimore area, if we look on the regional composite radar, it looks like it's already started to precipitate in DC and probably right on the doorstep in Baltimore. However, if you look to the left, to the Doppler radar that's just outside of DC, that's going to give you higher resolution and more quality data, you can clearly see that it hasn't started precipitating even close to Washington, DC, and it's probably several hours away from Baltimore. So it's quite a bit deceiving if we were just using a regional radar versus looking at a more detailed, finer and more accurate Doppler radar. And one of the reasons why this composite radar to the right is overdoing precipitation so much is it's blurring in the data that's coming from that southern radar site, which you see down here. And really what it comes down to is the further you are away from the actual radar site, the less reliable the data becomes. So as we've mentioned, those composite radars are made up of all these local Doppler radars. And there's over 140 of them throughout the US. Each one of those black dots represents where an actual Doppler radar is. Now, notice that a lot of the US is covered in this kind of lighter yellow, which generally means the radar data there is fairly quality. But once you get to those darker yellows, and particularly the blues, that's showing where the radar data is less reliable. And the reason being is that it's farther away from the radar sites at that point, which again makes it less reliable. Also notice if you look into the Mountain West, not only are there less radars, so the data is less quality, there's also mountains to obstruct those electromagnetic waves that we talked about before, which can further reduce the quality of radar coverage out in places like Utah, Colorado, and Nevada. A few things also that Doppler radars may struggle to detect would be very light precipitation, such as flurries or drizzle. So how far can Doppler radars reach, and why do I keep saying that they're less reliable, the data further away from the actual site itself? So what happens is the radar is oriented slightly up. It's not looking at what's at the ground, it's looking at a slightly higher angle above the ground. That base angle is only a ½ degree. It doesn't sound like a whole lot, but once you go 10, 20, 50 miles away from the site, that ½ degree angle adds up quite a bit. So if there's one thing that you can take away from this entire presentation, I want you to understand that radar is not detecting what is occurring at the ground, but rather it's at an angle above it. So to put that into perspective, let's look at a radar site in New Jersey at Fort Dix. That's where the white dot is there. And you can kind of see that white circle surrounding the radar, which is about 80 to 100 miles wide. That's about how far each of these radars can get at least somewhat quality data. Now, if we look into the image to the left, you can see what the radar looks like, and you can see that the electromagnetic waves that it's sending are slightly upward as you go out in distance. And to give a little perspective, if we use kind of our little ruler on the bottom, 20 miles from the radar, you're starting to look at 1,500 feet above the ground. So the radar is detecting what's happening 1,500 feet above the ground when you're 20 miles away from the radar site. That's really not that much, and usually what's happening at 1,500 feet above the surface is probably what's happening at the actual surface. Once you get 70 miles away from the radar site, you're looking nearly a mile up in the atmosphere, and a lot can change between 5,500 feet and the ground. And that kind of is why a lot of times the radar is misleading and might show you one thing versus the other. Is it's not showing what's happening at the ground, it's showing at what's happening above the ground. And to put this into some perspective, the radar site to Trenton is about 20 miles away. The radar site to WeatherWorks, which is where our office is in Hackettstown, is about 70 miles away. So anytime I stick my head outside and compare it to the radar, it may or may not be lining up just right because the radar is showing what's happening at 5,500 feet above the ground. And that kind of ties into the question of why is that not falling? And you see a picture of me acting very surprised that my radar shows snow, but nothing is falling. And the reason is it's called Virga. Virga is observable precipitation falling from a cloud, but evaporates before reaching the ground. So when the radar shows rain or snow, but it's not actually, you don't see anything at the ground, the radar is not wrong. The radar is showing rain or snow. It's just evaporating before reaching the ground. So when you're closer to the radar, because you're looking at what's closer to the actual surface, usually you don't see a lot of Virga, or you don't see a lot of funky things going on. But once you go further away from the radar site, particularly 40, 50 miles plus away from the radar, oftentimes what you see is not what you get. And Virga can happen at any time of the year. It's most common during the winter when the air is drier, and particularly at the beginning of a snowstorm. So there won't always be Virga. A lot of times what you see on radar is what is actually falling. But if you do see Virga, a lot of times it's at the beginning of a storm, and oftentimes in the winter with a very dry air mass in place. So here's a classic winter Virga example. We see a radar loop. This is about an hour long in a past February winter event. And it looks like in South Jersey, it's probably snowing pretty good. And most of Pennsylvania is snowing pretty well as well. In North Jersey and Central Jersey, it looks like they're just about to get in on the action. But if we actually stop this and freeze it, and we look to the right, one way to verify what's actually happening with radar is looking at airport observations. I'm going to talk more about this later. How can you get ground truth to make sure what you see on the radar is actually what's happening? And one way to do that is by looking at airport data. And what I've done for you, they actually tell you if it's snowing or raining or whatever. And the black line that you see there is essentially the snow, no snow line based on the airport observations. And on the left, I superimposed that over the radar site and over the reflectivity that you see, those greens and blues. So anything on the southern side of that is falling. But notice that all of this precipitation that the radar is showing through North Jersey and towards Allentown, all of that is not falling. That is all Virga. Even though it looks like Allentown's probably snowing pretty good at this point, they in fact are not. They're snowing pretty good at 4,000 or 5,000 feet, but there's plenty of dry air between that and the surface. And it's just going to take a little while for that to continue to saturate the atmosphere. And eventually, yes, it will reach the ground. And notice also that most of the Virga that you see is further away from the radar site. Once you get closer to that red dot, which is where the radar is, there's very little Virga. So again, closer to the radar site is going to give you a true representation of what's happening. Further away from the radar site, some funky things can happen and it can be more misleading. Here's another example of how rain and drizzle can kind of look different on radar and demonstrate how you're looking at different layers of the atmosphere when you're looking at a radar. So we'll start with this kind of heavier area highlighted by this blue arrow. That's moving from southeast to northwest, which is indicative of the mid-level flow in the atmosphere, somewhere between 10 and 20,000 feet in the sky. That's going to be a more mature rain, more moderate to heavy rain, and that's, again, falling from higher up in the atmosphere. Meanwhile, if you look towards the red arrow, you see this kind of lighter precipitation that's almost moving due east to west. That's indicative of low-level drizzle, which usually only happens a couple thousand feet above the surface. So it's not falling from 10,000 feet or 20,000 feet in the sky like the other rain that we talked about. It's falling from 2,000 or 3,000 or 4,000 feet from the sky and reaching the ground. So on this radar, it's a little bit deceiving, but one interesting thing that you may note is that it looks like the drizzle's magically disappearing once it reaches New York City or the Newark area. It's not actually disappearing. It's just that the radar beam is starting to overshoot the drizzle. So on this day, there was a plenty of drizzle all through North Jersey, all through even the Hudson Valley, but the radar beam starts to overshoot it once it goes away. So this is an example of how radar may underdo precipitation versus the last slide was Virga, where it may overdo precipitation. And that applies to also snow showers and freezing drizzle in the wintertime. Those are low-level phenomenon as well. So some additional winter weather uses. So before we get to the old rain snow line, why is my radar showing this when it's actually doing that? Let's just quickly touch on each type of precipitation. So snow is the obvious one, right? You have a snowflake in the sky. It's cold the entire atmosphere as it falls to the ground, and you get those snowflakes that build up and eventually need to be shoveled or plowed or salted or whatever. Raindrops, actually most of the time they start as snowflakes or some kind of frozen precipitation, but there's a big warm layer as it falls from the cloud, and it just falls as plain rain with minimal to no impacts during the winter time. Sleet and freezing rain is where it gets a little trickier. Sleet is literally ice pellets, and you can see this little slide as it hits the ground. You see it kind of bounce. So sleet is kind of like hail. It's a different process, but it's a similar idea where it's ice pellets falling, reaching the ground. It's that dense, nasty accumulation that's 3 or 4 times denser than the average snowfall. Meanwhile, freezing rain is straight up rain. It literally is rain that falls and hits the ground, but the surface that it hits is below freezing. So at that point, it turns into that glare ice. So again, freezing rain truly is rain that freezes on contact, whereas sleet are those ice pellets that are kind of, snow-ish in nature, but not really. So how can you figure out where the mixing line is, and why has your radar deceived you plenty of times in the past? So first thing, we're looking at a regional composite radar here, which again is nice for the big picture, but can be misleading and overdone because it's blurring in all those Doppler radars. As far as the precipitation type, there's no true algorithm on the radar that says definitively that this is rain, this is snow. There's algorithms and computer software that tries to mimic that, and they do a pretty good job for the most part, but it doesn't actually, the radar will not definitively tell you this is rain, this is snow. It's just an algorithm that tries to estimate it. And it's pretty darn good at this point, but there still are instances where it will be off. So don't trust it verbatim. Now, there is a better way to try to determine rain versus snow. This is probably the most technical part of this entire presentation, so I'll go through it quickly, but just so you are aware, there is something called dual polarization in a radar. And basically, about 5 to 10 years ago, NOAA developed this new technology, and it allowed us to look at the precipitation falling from the sky in both the horizontal and vertical direction. And basically, what that meant was we could see how light or heavy it was like the past, but we could also determine the size and shape of precipitation. So what we're seeing here in this kind of like pinkish yellowish radar loop is something called correlation coefficient. We're seeing how correlated the precipitation is, aka is it all snow because they're going to have similar shape, or all rain because they're going to have similar size and shape, or is it mixed in a low correlation where we have rain, snow, sleet, all of the above. So where you see the pinks and you see the purples, that's where it's pretty much all the same precipitation type. And where you see the yellows and the orange, you can clearly see that's where there's a whole bunch of different types of precipitation, and that's indicative of the rain-snow line. So if we were to interpret this correctly, we'd say, okay, to the north where it's all the same, those pinksy purple color, that's where the snow is. To the south, that's where the rain is. And in between, that's where the mixing line is. So it's something that we'll do constantly as meteorologists. We'll look at this as opposed to that rain-snow algorithm. You certainly can use the rain-snow algorithm. It's usually pretty good. But if you really want to get a little more technical with things, you could look at something called correlation coefficient. So we're not done yet, but I want to recap how you can better radar so far, and then we're going to tie in some other tools to supplement radar. So first off, yes, you can use that regional composite radar for the big picture, but use the Doppler local radars if you really want better detail and accuracy. So anytime you have to make a decision looking at radar, I would highly recommend that you just don't do it from the regional radar. You look at an actual Doppler radar site, and even that will be a little misleading at times, but it will be more detailed and more accurate. Now, obviously, you're going to need to know where the nearest Doppler radar site is located, as well as where some surrounding ones may be as well. Understand, and again, this is probably the #1 takeaway from this whole presentation, is radar is detecting reflectivity above the ground, and how high that is varies based on the distance from the radar site. So the closer you are to the radar, the closer it's showing to what's happening at the ground, so the more reliable it is. But the further you are from the radar site, the less reliable the data is. And that's where you're going to have at least be more prone to seeing Virga, where radar shows precipitation falling, but it's not reaching the ground, or it may overshoot those low-level snow showers and/or drizzle because the beam is going above where the precipitation's falling from. And then for more accurate rain-snow lines, if you want to get technical, you could use dual polarization. It's a setting within radar. Some apps will have it. And just be aware of the radar algorithms that show you the rain-snow line. Again, they're generally good, but by no means are they perfect. A couple of sources, if you want to screenshot or write these down, or I'd be more than willing, at the end you'll have my contact information. You can reach out to me for any radar suggestions or questions. But a couple of sites here. A free site is the College Due page, where you can get pretty much everything that I just showed you in pretty high resolution. It works well on both the desktop and mobile. There's a paid app called RadarScope. By no means is that affiliated with us, but most meteorologists do use for that on their phones for really high definition radar. And some additional sources would be the National Weather Service, which is generally okay, and WeatherTap, another paid source, which is where a lot of these radar frames were from this presentation. How does WeatherWorks use radar? So obviously, over the last 10 or 15 minutes, we've learned that there's a lot more that goes into radar than just straight up looking at it. You really have to be able to interpret it and understand what the data is telling you. So what we do and what you can do as well, and I'm going to show you how in just a few minutes, is we constantly combine our radar knowledge with actual ground truth to verify precipitation type, intensity, and the impacts to various surfaces. How do we do that, and how can you do that? Well, it's done through adding things such as satellites, webcams, social media, mesonets, getting reports from trained spotters, and you see a couple examples of that right here. You see a webcam with the road starting to cover with snow, and then you see some trained spotters here saying, hey, finally, light snow is falling. I'm assuming there was probably some Virga ahead of this, and these guys are finally saying light snow, it's starting to actually reach the ground, which is really helpful for us and can be very helpful for you as well. And here's a look at a storm center and kind of some of the things that we're going to have up at all times, which you can do as well. We have airport observations telling us if it's rain or snow. We have webcams. We have different radars. We have satellites. All these different things really help us understand what is actually happening. So bringing this back to you, having eyes at your site can be very beneficial and can be achieved through weather technology. So the easiest way to do this is looking at weather cams. And there's plenty of networks out there that you can look at weather cams for free. And you could even equip your own sites, and I'm sure a lot of your clients would be fine with this as well. You can equip them with weather cameras so you have visuals on those parking lots or those roads or those sidewalks or whatever it is at all times. And some weather cameras are equipped with not only air temperatures, they also give you an estimate of what the pavement temperature is as well, which can be extremely useful in the wintertime. You can get local airport data. Not just the big airports have quality weather data, the small ones do as well. And many of them offer 5-minute observations, an observation every 5 minutes, which can give you things like temperature, wind, and tell you if it's raining, snowing, or doing nothing. So again, it's ways to kind of get ground truth as opposed to just relying on that radar, which may or may not be fully reliable. And then you could also use a private weather service that can kind of do all this for you. Most of them are available 24/7. You pick up the phone, you call us, we'll tell you what's happening, or we can help you interpret that radar data or help you set up a weather camera or something like that as we go. So here's a couple examples of each. I'll start with a webcam example. This was from Connecticut, one of our clients out there. And we knew based on radar there was a pretty heavy snow shower that was going to move through. But we also knew that it was going to exit very quickly as well. So by looking to the right, we were paying attention to the road temperature data, which is what you see here in red. And we saw that it was previously 50 degrees and that it only would drop to about 34 degrees once the snow came through, and then it bounced right back to 35, 36. So we knew, yeah, hey, heavy snow shower is going to come through, and we could see that based on the webcam, but we also knew based on the pavement temperature that there was a very low chance to cover, and if it were to cover, it would melt right back. So that's an example of how webcams and pavement temperature can be very beneficial, and it's something you can do right from your office as opposed to having to have somebody on site constantly and see it for themselves. We mentioned airport observations as well. On the left, this takes a little bit of understanding how to look at this data, but these are all these different airports plotted, and they provide things like temperature data, dew points, wind, and then they're also telling you if it's snowing or raining. So we kind of have BDL highlighted just north of Hartford. Those little asterisks represent snow, and if you look a little bit south, those little big periods that you see there represent rain. But not only can you visualize airport data on a map, you could also see it site by site and see, okay, on the right, yeah, we've been snowing this entire time. It started at about 5:30. I see the temperature's been 33, 34. The winds have been this. This is all freely available data that is really, really helpful to see what's actually happening at the surface as opposed to just relying on the radar itself. And then, of course, if you don't want to have to do all this work for yourselves, or if you want some experts to help you along the way, there's private weather services out there that are monitoring your sites for you 24/7. I know we constantly are looking at that around the clock, looking at webcams, airport observations, radar, amongst some other things, and can help you make those critical decisions. When do I bring my crews out? Is it going to be a washout today with the rain that's starting? All those different things we can help you with. And as far as forecasts go, app-wise, most apps that you're looking at are literally just taking some model data and blending it together. So they may or may not be all that accurate, and there's very little human interaction. A private weather service will certainly help bridge that gap and give you a more detailed, better forecast that isn't just computer generated. But unfortunately, there's still no app for that. And in the wintertime, we're still going to need lots of people shoveling, plowing, whether it's roads, sidewalks, parking lots, all of the above. Technology is improving, and I know there's some kind of automatic ways of doing plowing in parking lots, but I don't foresee anytime soon an app to completely take care of that.
Yeah, great. Thank you so much, Rob. Great presentation, and I hope everyone found the information you presented very useful to take back with you and out in the field. But right now, we'll open up the floor for a few questions. I know we had a couple come in throughout the webinar, so if you do have any questions, feel free to ask them on the right-hand side of your screen. So one thing, we've had several people ask where they can get webcam and airport information. Do you have any suggestions for these folks?
Yeah, I mean, there's a couple different sites. So a lot of road departments, if you look on like their travel site, they'll actually have road webcams that'll generally be on the major interstates, so they may or may not be representative of what you're necessarily treating, like a shaded sidewalk or a parking lot. But those are pretty freely available. Rattling off links right now probably isn't the easiest thing. I would recommend just shooting me a question and I can provide you some links. There's also some personal weather stations. Weather Underground, if you use their Wonder Map interface, there's a whole bunch of webcams on there as well. And as far as the airport data goes, I had a link on a few slides ago, but again, probably the best way if you are interested in using that, just shoot me a quick email. I'd be more than happy to provide the links and even help you try to set up some things and tailor it to your needs.
Great. This next question comes from John, and he was asking, how do you account for Virga in your forecasts?
Yeah, so when we're making a forecast, there's a couple different ways, but straight looking at a radar won't necessarily help you, right? You can infer that it is or isn't reaching the ground, but without that actual ground truth, such as webcams and airport obs, and actually looking for trained spotters and communicating with some of the people that help us with that ground truth, it's very difficult to do. When we're making a forecast, we'll look at different things on models. We'll look at something called a sounding as well, where we're actually looking at the entire atmospheric column and seeing where it's saturated and not saturated. So if there's a really big dry layer near the surface, we know that, yeah, precipitation might start on radar, but it's probably going to take a little while to actually reach the ground. So we're looking at a whole bunch of different things, but it is accounted for when we're making forecasts.
Awesome, great information. This question comes from Joe, and I know we didn't touch on this topic much, but it may be relevant to some of our folks listening out there. And he's curious, how do radars find tornadoes?
It's a little more technical, but what you'll look at for tornado on radar, if you're just looking at the reflectivity like you're used to, which is those greens and yellows and reds, you're starting to look for small little rotation in that. And if you look at something called velocity, one thing that radars can do that we didn't touch on is you can literally look at how quick the raindrops are approaching or moving away from the radar site. So if we start to see that there's some rotation, some are moving right towards the radar site, some are moving away from the radar site, and there's a big differential there, we can infer some rotation, which would increase the potential for tornadoes. So essentially with the reflectivity, you're looking for something called a hook echo, which is a little bit of rotation that you can kind of see spinning on the radar. And then you're also looking at the velocity and looking for the velocity. It's called a velocity couplet, where there's a high differential between the incoming and the outgoing velocity on that.
Awesome, great explanation. And as always, if anyone does have questions, obviously on any upcoming weather, if you do have a private weather service like ourselves, always welcome to give us a call if you have any concerns with what's showing up on the radar. One other question we had was if people will be receiving a copy of today's presentation. We will be sending one out here later this afternoon, so if anybody missed anything or would like to review the webinar, we'll have one in your email here later today. So actually, one last question here. How often are aviation maps updated with new weather? That's a great question coming from Jesse.
Yeah, so the airport obs maps, they update at minimum once an hour. I guess I can go back to it real quick. So this map that you see here on the left is updated at minimum once an hour. Sometimes it's more frequently. It sort of depends on the weather that's going on. So yeah, they won't be more than an hour old. And usually if it's starting to precipitate or something's changing is when they'll update more frequently. But like I said, if you want to look at each airport individually, there are ways to see those every 5 minutes, regardless of what's actually happening. So kind of a two-part answer. The map, usually at minimum once an hour, can be less, but the actual observations, you could look more frequently at a 5-minute interval if you choose to do so.
Awesome. Thank you, Rob. Well, that about wraps up our webinar for today. Any sales-related questions that we're unable to answer at this time, they can always be submitted to sales@weatherworksinc.com. And you may also get in touch with Rob at robreale@weatherworksinc.com. As always, we are available around the clock through our company line, 908-850-8600, or online at weatherworksinc.com. So just want to thank you folks for joining us today, and you have a wonderful afternoon. We hope to see you guys next time.
Thanks, everyone.